Keats. I know you probably just want to listen to that again. So ready? Ha! No, just kidding. All right. So we're gonna do a practice problem. A girl, she is running 5 meters per second tangentially. Tangent to the circle towards the edge of a 40-kilogram merry-go-round with a radius of 3 meters. We're going to say I for the merry-go-round is this because we're going to pretend the merry-go-round is a solid disc. She's going to hang on to the outside, and we want to determine her angular speed after. Now, there's a couple of assumptions we have to make. The first assumption is going to be, we're going to assume that the girl size, her size, not her mass, but her size is small compared to 3 meters, okay, which is probably true. So that we're going to treat her like a point mass. So how do I do this? Well, I first draw a picture. So here is my merry-go-round. Here is my girl, and she is running 5 meters per second towards the edge. Then, for my after side, she has jumped onto, and they're going to rotate together. So it's going to look something like this. Okay? All right. So, first of all, hopefully you understand it's a collision. Anytime you're dealing with a collision, you have to deal with momentum. Why? Because anytime you have a collision, there's going to probably be some heat that's produced. And it's really impossible to figure out how much heat is produced until you do conservation of angular momentum. So we're going to write our equation before, we're going to write our equation after. So does our merry-go-round have angular momentum? It does not. Does our girl have angular momentum? She does. Okay. Why? She's moving straight. Well, the reason she has angular momentum is that afterwards your system, the merry-go-round girl system, has angular momentum. Therefore, beforehand, your system has to have angular momentum. If you would like more information on why something moving straight can have angular momentum, watch the instructional video. Okay? But so I have the girl times omega of the girl. Over here, I would have I of the merry-go-round plus I of the girl times my new omega. And then, since there's no outside things doing torque, set them equal. So far so good? All right, so let's plug stuff in and solve. I is going to be mr squared for the girl. Okay. This would be, hey, I'm going to draw my circle. D equals 2 pi r. Theta equals 2 pi. D equals theta times r. V equals omega times r. Omega equals v divided by r. Remember, we're not memorizing things. We are understanding things. Okay. All right. But so this is going to be v divided by r equals, if I do a little math, goodbye r. One of the r's go away. And then over here, I'm going to get 1/2 mr squared plus, again, mass of the girl, r squared times omega 2. And then it's just a matter of I got to plug numbers in. Okay? So let's plug numbers in. Mass of the girl is 20. 20. The radius of the girl, right before she hits, is going to be 3 meters away. 3. The tangential velocity is 5. Over here you would have 1/2. The mass of the merry-go-round is 40. The radius of the merry-go-round is 3. Okay. Mass of the girl is 20. The radius is 3. And then omega 2. And then we have to solve for omega 2. And let's do a little bit of algebra. 20 times 3 times 5, that's 300, and then, so 40 times 1/2 times 9, plus 20 times 9, so I want to take 300 divided by 360, and I get 0.83 radians per second, and then, because I'm asking for speed, I don't need direction. If it was velocity, it would depend on my picture, and my picture shows it would be going counterclockwise, but hey, it's speed, so there we go. Bye, kids!